Fine, good morning to everyone. This is Jakudipti of Branch Aeronautical Engineering, bearing rule number 23951A2114 of semester 6. Today I am here to give presentation on behalf of AIT Concept Video or AIT2. Subject Finite Element Method. The topic I have chosen is heat transfer in rocket nozzles. Getting into the introduction. Background. Rocket propulsion system operates under extreme conditions involving high pressures. The rocket nozzle plays a crucial role in converting thermal energy of combustion gases into kinetic energy, producing thrust. During this process, the nozzle is subjected to intense heat loads due to the high temperature gases flowing through it. Importance of heat transfer. Heat transfer in rocket nozzles is a major concern because excessive heat can damage the nozzle structure. The temperature of gases inside the combustion chamber can exceed 3000 Kelvin, and as these gases expands through the nozzle, they transfers heat to the walls. If not properly managed, this heat can lead to material failure, reduced efficiency, and shorter operational life. Modes of heat transfer. Three primary modes of heat transfer occurs in a rocket nozzle. The first one is conduction through the nozzle material. Then coming to second one, convection between hot gases and the nozzle wall. Coming to third one, radiation from high temperature gases. Among these, convection heat transfer is the most significant one. Challenges in rocket nozzle design are: designing a rocket nozzle requires careful consideration of thermal stresses, material selection, and cooling techniques. The throat region experiences the highest heat flux, making it the most critical part of the nozzle. Engineers must ensure that the nozzles can withstand these conditions without failure. Role of CFD in heat transfer analysis. Computational fluid dynamics is widely used to simulate heat transfer in rocket nozzles. It helps in predicting temperature distribution, heat flux, and flow behavior. This allows engineers to optimize nozzle design and cooling methods. Now coming to the objectives of this project. The main objective of this study is to analyze heat transfer characteristics in a rocket nozzle and evaluate methods to manage thermal loads effectively. Study of heat transfer mechanisms are: the study aims to understand conduction, convection, and radiation processes occurring within the nozzle. Special emphasis is given to convective heat transfer as it is the dominant mode. Temperature distribution analysis. Another objective is to determine temperature variation along the nozzle length. This helps identify regions of maximum thermal stresses, especially near the throat. Heat flux evaluation. The study focuses on calculating heat flux along the nozzle wall. This information is crucial for designing effective cooling systems. Evaluation of cooling techniques are: different cooling methods such as regenerative, fill, and ablative cooling are analyzed. Their effectiveness in reducing thermal loads is compared. Methodology. The first one is geometry creation. The first step in the methodology involves creating a precise geometric model of a converging diverging CD rocket nozzle. The geometry is designed based on standard nozzle design principles, ensuring smooth curvature between the converging throat and diverging sections. The throat region is given special attention since it is the most critical area in terms of heat transfer and flow acceleration. The geometry can be created using CAD software such as ANSYS Design Modeler or SolidWorks and imported into ANSYS Fluent. The dimensions are selected based on desired operating conditions such as cambered pressure, temperature, and mass flow rate. Next, coming to mesh generation. A high quality mesh is generated to accurately capture both fluid flow and heat transfer characteristics. A structured or hybrid mesh is preferred for better accuracy and convergence. The mesh is refined near the nozzle wall and especially around the throat region where steep temperature and velocity gradients exist. Inflation layers are applied along the wall to resolve the thermal and velocity boundary layers effectively. The first cell height is chosen to maintain an appropriate Y plus value, typically less than 1, for high accuracy in heat transfer simulations. Grid independent studies are also performed to ensure that results do not vary significantly with further mesh refinement. Next, boundary conditions. Proper boundary conditions are essential for realistic simulation of heat transfer. At the inlet, high temperature and high pressure combustion gases are specified, typically using total pressure and total temperature conditions. The outlet is defined as a pressure outlet with ambient pressure conditions. The nozzle wall is treated as a no-slip boundary, meaning the velocity at the wall is zero. Thermal boundary conditions are applied in the form of either constant wall temperature or convective heat transfer coefficients, depending on the cooling methods being analyzed. In some cases, coupled wall conditions are used to simulate heat conduction through the nozzle material. Setup solver. A pressure-based solver is selected for simulation suitable for compressible flow conditions at moderate Mach number. The energy equation is enabled to account for the heat transfer effects. Turbulence models such as K epsilon naught and K omega SST are used to capture turbulent flow behavior inside the nozzle. For more accurate heat transfer predictions, especially near the wall, the K omega SST model is preferred due to the better near wall treatments. Second order discretization schemes are used for moment, energy, and turbulence equations to improve solution accuracy. Material properties such as thermal conductivity, specific heat, and viscosity are defined as temperature dependent to reflect real gas behavior. Simulation procedure. The solution is initialized using hybrid initialization, which provide a balanced starting point for both pressure and velocity fields. The simulation is run iteratively and convergence is monitored using residuals for continuity, moment, energy, and turbulent quantities. In addition to residuals, physical quantities such as wall heat, flux, and temperature are monitored to ensure solution stability under relaxation factors and adjusted if necessary to achieve smooth convergence. In some cases, transient simulation may be performed to study time-dependent heat transfer effects. Post-processing. After achieving convergence, the results are analyzed using post-processing tools available in ANSYS Fluent. Temperature contours are examined to identify regions of high thermal loading. Heat flux distribution along the nozzle wall is plotted to determine critical zones, particularly near the throat. Velocity and Mach number contours are also analyzed to understand flow acceleration and expansion. Graphs of temperature variation along the nozzle length provides insights into thermal gradient. These results helps to evaluating the effectiveness of cooling methods and identifying potential failure regions. The results and discussion includes temperature distribution. The result shows the highest temperature occurs near the combustion chamber and the throat region. Heat flux analysis. Maximum heat is observed at the throat due to high velocity and temperature gradients. Effects of cooling techniques. Cooling method significantly reduces wall temperature. Regenerative cooling is found to be most effective. Flow behavior. The flow accelerates the nozzle, converting thermal energy into kinetic energy. Thermal stress regions. Critical regions are identified where thermal stress is highest. These areas require special design attention. Conclusion. At last, I would like to terminate this project by saying that the study of heat transfer in rocket nozzle provides a comprehensive understanding of the thermal challenges associated with high-speed propulsion system. Rocket nozzles operate under extremely harsh conditions where combustion gases at very high temperature and pressure expands rapidly to produce thrust. This process exposes the nozzle walls to intense thermal loads, making heat transfer analysis a critical aspect of nozzle design. The present study successfully examined the various heat transfer mechanisms including conduction, convection, and radiation, with particular emphasis on convective heat transfer, which is the dominant mode in rocket nozzles. Thank you. Thank you for giving this opportunity.